Hi, hello everyone. This is Dr. Brahmayya, Associate Professor, Department of SNH Chemistry, MLR Institute of Technology. Today I am going to talk about electrode potentials. So, electrode potentials and standard electrode potential. We can talk about these two topics today. Electrode potential and standard electrode potentials are regarded as the key principles of the electrochemistry. Without these terms, without these definitions, we cannot move in the electrochemistry. So the students must be understand about these two terms. Otherwise, we cannot understand the complete electrochemistry. So what is electrode potential? The potential difference between an electrode and an electrolyte solution, which is a measure of the tendency of an element to be oxidized or reduced. What is that? We have to know that the electrode potential, the potential difference between an electrode and electrolyte. Electrode, suppose one electrode is here and this is dipped in some solution like copper sulfate or zinc sulfate, something like that. In this electrode, in this system, a measure of the tendency of an element to be oxidized or reduced. The electrode is suppose zinc or copper. So, whether it is oxidized or reduced, the tendency of this metal atom, oxidation of the metal atom or reduction of the metal atom, it can show you the electrode potential. So, how much of electrons it loses, how much of electrons it gains. So, we have to know the tendency of this electrons gaining and electrons losing. This is the potential difference, which will be potential difference we can know. Standard electrode potential E0. It is electrode potential is simply it is E. Standard electrode potential E0. The potential of an electrode measured at standard temperatures 298 kelvins and 1 molar ionic concentration. With the standard hydrogen electrode SHC, standard hydrogen electrode assigned a potential of 0 volts. So we have to say about for the standard electrode potential, we have to apply the conditions like the standard measure, the standard solution is 1 molar and the temperature is 298 kelvins, whereas the standard hydrogen electrode potential is 0 volts. At these conditions, if you know the measurements of any electrode with this reference, this is called standard hydrogen electrode. We will discuss even more in further. So, electrode potential. You look into here in this figure. When a metal rod is dipped in its salt solution, like for example, a zinc rod is dipped in the salt solution, electrolyte, salt solution is electrolyte, and the metal atom tends either to lose electrons oxidation or to accept electrons reduction. So, the metal atom from the electrode, whether it is going to lose electrons, whether it is going to gain electrons, it is electrode potential. The tendency of the electrons losing or gaining of the electrons is called electrode potential. Even further, the process of the oxidation or reduction depends on the nature of the metal. The process of the oxidation or reduction depends on the nature of the metal. And in this process, there develops a potential between the metal atom and its corresponding ion called the electrode potential. So, this is the electrode. It is Zn zinc sulfate. Suppose zinc sulfate is there, electrolyte and zinc 2+ ions. So, electrolyte and metal, between the metal rod and electrolyte, how much electrons are losing, how much electrons are gaining, how many electrons are gaining. So, this is the concept, the tendency of the electrons are gaining or losing, which is called electrode potential. If you look into copper sulfate, electrolyte is copper sulfate, copper rod dipped in the copper sulfate, you can find out the electrode potential. Zinc metal in zinc 2 plus solution, copper metal in copper 2 plus solution. So it is a measure of the tendency of metallic electrode to lose or gain electrons when it is in the contact with its own ions in solution with reference to the standard hydrogen electrode. So we have to take the reference electrode, standard hydrogen electrode. By comparing with that one, we can find out the electrode potential. Reduction potential. The tendency of electrode to gain electrons and to get reduced is called reduction potential. Its value is plus x volts. Its value is plus x volts. So as we know in the previous slides also, the tendency of the electrons that gained by any metal, it is called reduction. Oxidation potential. Similarly, the tendency of an electrode to lose electrons and to get oxidized is called oxidation potential. Its value is minus, negative volts. It is assigned as negative sign. The potential developed between the electrode and electrolyte by the formation of the charges, and these charges are formed Helmholtz electrical double layer through which potential developed between the electrode and electrolyte. The potential development between the electrodes and electrolyte. The total cell EMF, electromotive force is equal to the sum of the single electrode potentials. So two electrodes are there. If any cell, if any electrolytic cell or galvanic cell, it is involved by two electrodes or three electrodes, we have to calculate by each individual electrodes potential. Then we have to make them sum. Then we can come to know the EMF, electromotive force. Each electrode is affixed with a symbol corresponding to the reaction that takes place near to the electrode. The half cell reactions are as follows. Half cell reactions. Oxidation reaction is one half and the reduction reaction is one more half, which corresponds to the oxidation is as follows. We can see in the next slide. For example, zinc metal will lose its electrons Zn2 plus and 2 electrons. The electrode is called oxidation electrode and the potential of the electrode is oxidation potential, or the potential of the left hand electrode, which is represented as E subscript oxidation, E subscript left, or left hand side reactions electrode potential or right hand side electrode potentials. So the cell reaction of the electrode where reduction takes place is given below. Ce2 plus, it's a cathode. 2 electrons gain, it becomes Cu. So Zn 1 electrode and Cu 1 electrode. It oxidizes. Oxidation takes place here and reduction takes place here. Zn, this is Zn 2 plus 2 electrons. These 2 electrons gained by Ce2 plus ions become Cu. The electrode is called reduction electrode or right hand electrode, and the potential of this electrode is reduction potential and represented as E subscript reduction, E subscript right hand side. So at cathode, it's a left side and right side. Left side is like oxidation, right side is like reduction. The total cell reaction is Zn plus Cu2 plus gives rise Zn2 plus Cu. Total overall cell reaction is E is equal to E oxidation plus E reduction. This is the overall reaction equation. This is the overall EMF. EMF of the cell is equal to the sum of the oxidation potential and reduction potential as we just discussed. Also expressed as the reduction potential of the right hand electrode minus reduction potential of the left hand electrode. So the potential difference between, though we are having a two electrodes, one is cathode, one is anode. Though we are having a two electrodes, each individual electrode is having its own highest oxidation property and its own lowest reduction property also. So we have to calculate the one single electrode's highest oxidation state or highest oxidation process, how many electrons it is gaining, and the lowest possibility of the reduction state. We have to find out this difference. This is the actually electrode potential. Mathematically, EMF or E cell, E cathode minus E anode, or E cell is equal to E right minus E left. So we are going to find out the EMF of any electrode. We have to consider of the particular cathode or anode. Against to its major property, we have to also consider its minor property, which is like oxidation or reduction. Then we can come to know very easily about these mathematical equations. Where E cell is equal to EMF cell, overall electromotive force, and E right, reduction potential of the right hand side electrode cathode, and E left, reduction potential of the left hand side electrode anode. And E cell is equal to E oxidation plus E reduction. This is overall EMF. E cell, E reduction minus EL, both are reduction potentials. So it implies that it is considering one electrode they are considering. They are talking about electrode reduction, and electrode oxidation, left side and right side. How much its potentiality in the only one term of the oxidation or only one term of the reduction. Then this difference we have to calculate. Again we can write E cell is equal to E left minus ER cathode. Both are oxidation potentials. So we are considering both are oxidation potentials. Here we are considering both are reduction potentials. Two electrodes are having two different properties. Both are having oxidation process and it is also having a reduction property. So we are also considering its lowest reduction property. So we have to consider that one. If you don't consider that one, we cannot understand these equations. Note, in electrochemistry, EMF stands for electromotive force, which is the maximum potential difference between the two electrodes of an electrochemical cell when no current is flowing. It is a measure of the cell's ability to perform electrical work and represents the net voltage arising from the oxidation and reduction half reactions within the cell. Standard electrode potential E0. Standard electrode potential, when the electrochemistry is representing E0 or delta G naught, something like that, it's a standard procedure methods. These are the representation for the zero is standard conditions. So standard electrode potential E0 is the voltage of an electrochemical cell measured under the standard conditions 298 kelvins, 1 atmospheric pressure and 1 molar concentration for a half cell reaction compared to the standard hydrogen electrode SHE, which is defined as 0 volts at standard conditions for a SHE. It quantifies a substance tendency to gain electrons be reduced with more positive values indicating stronger oxidizing agents and more negative values indicating stronger reducing agents, helping predict reaction spontaneity. So, for example, Cu2 plus by Cu gives rise to E0. At standard conditions, so how much reduction is happening, how the reduction is happening, how many electrons are transferred, we have to check like that. How it is oxidized and how it is reduced. When concentrations of the Cu2 plus is 1.0 molar and E0 value of the single electrode is determined experimentally by combining the single electrode with the standard hydrogen electrode. So these are the things: spontaneous reactions and non-spontaneous reactions. So for spontaneous reactions, galvanic cell is one of the best example. The reactions will be happened without an extra force. For non-spontaneous reactions, it's a electrolytic cell which needs an extra force to drive the reactions forward. So that is electrolytic cell. That is non-spontaneous reactions. So it can be standard oxidation potential or standard reaction potential. It is denoted as E0 and expressed in volts. If oxidation standard oxidation potential, then denoted as a E0 oxidation. If reduction standard reduction potential, then denoted as a E0 reduction. And E0 cell is equal to E0 right minus E0 left. This is the formula. E0 right, standard reduction potential of the right hand side electrode cathode, and E0 left, standard reduction potential of the left hand side electrode anode. This is the left hand side, this is the anode, this is the right hand side, it's a cathode. So this is the one cell. If you look into this one, this is a galvanic cell. It is zinc and it is standard electrode hydrogen, standard hydrogen electrode. This is, with the reference of this SHE, we are going to find out this zinc electrode potentials in different cases. So key aspects. Reference point, the SHE, platinum electrode, 1 molar H+ ions and 1 atmospheric H2 gas serves as the universal 0 point. So this is the standard hydrogen electrode. Conditions applied. E0 values are specific to standard conditions of 298 kelvins, 25 degrees centigrade at temperature, and 1 atmospheric pressure and 1 molar concentration of unit activity, concentration for the all solutes. Measurement, measured as the potential difference between the electrode of the interest and the SHE, standard hydrogen electrode. Interpretation, positive electrode, the species is easily reduced to stronger oxidizing reason, and the negative electrode, the species is easily oxidizing stronger reducing reason. Very simple. And applications, used to calculate the cell potential E0 cell for the spontaneous reactions and non-spontaneous reactions. E cell greater than 0 is a positive, it's a non-spontaneous in galvanic cells, spontaneous cells, where the more negative E0 half cell becomes the anode. Examples for values reduction reactions. F2 plus 2 electrons gives rise to 2F minus electrons plus 2.87 volts strongest oxidizer. This is one of the example. Lithium plus electrons gives rise to lithium. It is a happening of reduction minus 3.04 weakest oxidizer and stronger reducer. Zn2 plus 2 electrons gives rise to Zn and minus 0.76 volts. The measured value is minus 0.76 volts. Copper 2 plus 2 electrons gives rise to Cu plus 0.34 volts. These are the values, measured values for the spontaneous and non-spontaneous reactions. In summary, the presentation covers the electrode potential and standard electrode potential for the accurate measurement of the energy transformations of the electrochemical reactions. These are the fundamental things what we have to know today in this particular topics of the electrochemistry. Introduction part and further definitions of the important topics like reduction and oxidation. Thank you.